Alright everyone, we're going to go ahead into section 2 of our unit. And, like I said, you'll notice a lot of the information goes kind of quickly. So you want to make sure that you are paying attention, that you're keeping up with your notes, and writing down any questions that you have. Also, my hope is that you realized in the guided notes that I gave you that at the end there were 2 summary questions that were left for you. Make sure that you answer those. Those are a part of the packet and a part of the overall grade. If you want to get the points for this for this packet, you need to make sure you complete those questions. Now, let's go ahead and dive in. We have a scale, of course, that we're going to start off with. The goal, of course, is always going to be score 3.0. The goal, that is our learning goal. Without using notes, students are able to distinguish between polar and nonpolar molecules and explain the factors that cause attractions between molecules. So let's jump right in. Now, there are 2 types of covalent bonds. There's nonpolar covalent bonds, where the electrons are shared equally, and there are polar covalent bonds, where they're shared unequally. A polar bond, unequal sharing of electrons between 2 atoms. One example we can look at here would be one like HF, or hydrogen fluoride. Now, in a polar covalent bond, one atom typically has a partial negative charge, and the other one ends up with a partial positive charge, just because of how these electrons are being pulled. So looking at the diagram here, I have hydrogen and bromine here at the bottom of the screen, and bromine has a much stronger electronegativity. Remember that term that we talked about before? Now, because of that difference in electronegativity, let me go ahead and write this in. Because of that difference in electronegativity, we're going to have a tug of war that breaks out. Oops, that's an I. Now, because of the fact that there's a tug of war going on, the electrons are going to go in the direction of the one that is the strongest. We talked about our trend for electronegativity. We said that the higher values are going to be on the right and towards the top. So bromine is going to end up being higher, stronger than hydrogen is. Because of this, it's going to have a little bit more of a pull on those electrons overall. Now, nonpolar covalent bonds are going to be equal sharing of electrons between 2 atoms. Some examples here given are Cl2, N2, and O2. Now, this is tug of war, but again, it's between 2 sides that are basically about the same strength. Now, just giving you an idea of what's going on overall, comparing this to what we had for our, bring this up, from our ionic all the way through our covalent and polar covalent. For ionic, we had the actual transfer of the electrons. So you notice that we have 2 atoms, but they're separate, this one having both electrons taken care of. Now, in a covalent, or a nonpolar covalent compound, let me go ahead and write that up above it. This is a nonpolar. Now, in a nonpolar covalent compound, you notice that they're equally shared, so they have some overlapping, but they're holding on to those electrons equally. This would be the same as most of our diatomics, or even the some of our different elements that are participating as well. Now, when we come to our polar covalent bond, you notice that, okay, now these electrons are pulled a little bit further into the other atom. This causes it to have this partial positive, partial negative charge. A symbol that you may see me draw in class, and just so you can understand what it is, some people say it looks almost like a cherry or a cherry bomb. This is a sign meaning partial. So if you ever see me draw that sign, just know it means partially positive or partially negative. Now, when it comes to these attractions between molecules, the biggest thing we need to understand that outside of the interactions that happen within the molecules, like ionic, metallic, and covalent bonds, there are also going to be times where the molecules are attracted to each other. These intermolecular, notice the word in that word, intermolecular attractions are going to be much weaker than ionic, covalent, and metallic bonds. So these are not on the same scale, they're not on the same level, but they are going to be a factor when we look at a lot of other things down the line. When we look at boiling point, when we look at melting point, when we look at interactions within reactions. Now, if you're looking at the diagram we have here, we have here HCl is being attracted or has an attraction between another HCl molecule. This is where we talk about that weak reaction. Now, there are two main types that we're going to deal with. There are van der Waals forces, which are usually going to be the weaker side of the intermolecular forces, and we have hydrogen bonding. We're going to mainly spend our time with hydrogen bonding. We'll talk about the other was London dispersion and dipole in class, but the main one that we're going to focus on, because it has so many applications to everyday life, is going to be hydrogen bonding. Now, hydrogen bonds are forces where a hydrogen atom is weakly attracted to an unshared pair of electrons from another atom. Okay, so this is not happening in the same atom. This is between two separate atoms. Now, this is going to be the strongest of our intermolecular forces. Okay, now notice this other atom must be in a nearby molecule and has to include a hydrogen. It's only possible because of the fact that hydrogen has some things that are a little different. When we draw our hydrogen Bohr diagram, we have a ring with one dot. Okay, I apologize for that. Now, if hydrogen is interacting with another electronegative element, say fluorine, which on its outer ring has 7 dots, fluorine has a much higher electronegativity value. So when it pulls this electron, let me go ahead and erase my electron from here. When it pulls that electron, it's going to pull it more on this side. So it's still being shared, but most of the strength is over here. Now, when we look at the fact that hydrogen's nucleus is electron deficient at that time, or it's lacking electrons once it gets pulled a little bit further, this is what's going to cause that strong, slightly positive charge that we talked about, whereas fluorine is now going to be slightly negative. Okay? Now, usually this is going to happen when hydrogen is with another highly electronegative element. So mainly nitrogen, oxygen, or fluorine. Those are the big three that we'll look at. Oops. Now, if I can get rid of the other stuff that I have here, this is going to be responsible for what we call surface tension. So if you ever saw water striders or looked at the fact that when you fill a cup up with water, maybe you're washing dishes and you got bored and you filled it up and you kept filling it, and you noticed that it will build up on top of itself instead of just falling over. This is the force that's actually responsible for that. And again, as I stated before, this is going to be the strongest of all of the intermolecular forces that we'll deal with. So now, last thing to go, naming molecular compounds. Now, why did I save this for last? Because it actually is very, very easy. We're going to utilize some different prefixes to say how many atoms or how many of that atom are involved. So these are all, I think, based in Latin. So mono, di, tri, penta, tetra, penta, hexa, and so forth. We've dealt with those before. Now, if there's only one atom in the first element in the compound, there's only one of them, we don't have to use a prefix. But if there's more than that, we do have to use them. So in the example we have here, we have a carbon atom and we have an oxygen atom. So carbon monoxide, mono meaning one, oxide, just like we did before with our second ending, our second element, we changed the ending to IDE. So that part's not too bad. Another example, given the formula N2O3, this will be di, nitrogen, di because of the 2, as you see here, nitrogen, tri, because there are 3, oxide, 3 oxygen. So the formula basically tells you the name, and the name tells you the formula. You're looking here, sulfur, there's only 1, so no prefix. Hexafluoride, there's 6, so hexafluoride, not a problem. Now, at this point, I want you to go ahead and look back at your information, and I want you to determine where you are on this scale. How do you feel about this information? Once we come into class, we're going to spend a little bit more time with it, but also we're going to see this information as we prepare for the test. So I want you to take your time, look through your notes, get everything set so that there's no confusion about what's going on in class. Now, if you have questions, write them down. Please write them down on the page and bring them into class so we will be able to answer them. I don't want anybody to be lost or not understanding what's going on. So have a good evening. I'll see you in class, and